Let's continue our review. Let's talk about rational expressions. We're going to review a rational expression. Actually, it is a fraction of one polynomial over another polynomial. So a rational expression basically is just a fractional algebraic expression. We have a polynomial in the numerator, we have a polynomial in the denominator. That's called a rational expression. So let's take a closer look at the domain of rational expressions, because when you start putting variables in the denominator of a fraction, you start messing up what value that variable can be. For instance, now remember, domain is the set of all numbers for which you can input that number in for the variable and you get a well-defined unique output. That's what makes a function, right? So the domain of functions is going to become very important to us. So let's say we have this rational expression right here, 1 over x. Well, we're going to be fine for any x value that we want to put in that expression. We're going to get a well-defined, real, unique output for any input that we put into this expression except 0. So usually when we start talking about let's find the domain of this function, we look for where we might have a 0 in the denominator or where we might have a negative under a root sign. We usually look for values that we have to throw out of the set of all real numbers instead of trying to chase the infinitely many real numbers that will be in that domain. So domain becomes more and more and more important for us as we go on, and most especially when we're dealing with rational expressions. So find the domains of the following expressions. Well, this is a polynomial, not a rational expression. No fraction, no denominator going on here. There isn't any real number that I can't put in here for x and not get a well-defined unique output. So the domain for this trinomial, for this expression, is all real numbers. Let's see, I think I've got, yeah. So the set of all real numbers will define the domain for any polynomial as long as we don't have a term that has a variable in the denominator. So let's look at B. We had this rational expression. We have a polynomial in the numerator. We have a polynomial in the denominator. So our domain is going to be affected by whatever values we're going to get when that denominator equals 0, because you can't divide by 0, the world will end, right? So we're going to factor it. We're going to set each factor equal to 0, and we're going to know that we have to throw x equal 2 and x equal 3 out of the full set of real numbers, and every other real number will therefore be the domain of this function. And let's look at the last one. We're going to have issues in the numerator if we put negative values in here. Now, it's okay for it to be 0. The square root of 0 is 0. The nth root of 0 is 0. But we cannot, if we're looking for real numbers and we want to stay in the real realm and not go to the complex realm, we can't have negative inputs under that radical sign. So the numerator is forcing us to throw out every negative number that there is. Now, the denominator is only forcing us to throw out one value of x, where that denominator would equal 0, and that's the value of 5. So the domain can be all positive numbers. It can be 0, but it can't be 5. No negative numbers and no number 5. Simplifying rational expressions. So we know a lot about multiplication. All rational expressions do is take our knowledge of what's going on with multiplication and pull it over to have it work on division. So anytime that we are multiplying by the same thing, numerator and denominator, you have to realize we're multiplying by a value of 1. I don't like this word cancel. I have too many students that I've had in the past who are like, oh, well, this cancels. And I ask them why, and they look at me dumbfounded. I don't know, because you can't have the same thing in the numerator as the denominator. Well, here's why it cancels, because that's multiplying by a value of 1. A times C over B times C is A over B times C over C. And that's going to give me A over B times 1, which gives me A over B. So the whole canceling idea works. That is, in essence, what's going on. But when we have to go later on and reverse this process and come up with these well-chosen ones, I want you to definitely have the idea in your head, we're multiplying by 1. And it cancels because it has a value of 1. We're replacing it by writing times 1. Okay, so the whole cancel idea is, I mean, it's a good one. I understand it, but I definitely want you to see the idea that you're multiplying by a fraction that has a value of 1. That's going to come in handy for us later on down the line. So you could factor the numerator, factor the denominator. If the same factor is in the numerator and the denominator, then that ratio has a value of 1. You, quote, cancel it, and then you have simplified your rational expression. So multiplying and dividing rational expressions. We can multiply straight across, right? Numerator times numerator, denominator times denominator. Multiplication couldn't be more straightforward. So if I'm multiplying this numerator times that numerator, then that's exactly what I'm doing, and this denominator times this denominator. I don't cross any lines or cross multiply or anything like that when I'm just multiplying rational expressions. So this is just kind of like our work we did in the last lesson where we're just multiplying a trinomial with a binomial. And we know how to do that. And then if you have like terms, again, that has a ratio value of 1, so they cancel out. And division couldn't be easier because we take the first fraction, flip the second fraction, and then do what we just did, just multiply straight across. So if we are dividing one rational expression by another, we usually take that second rational expression and invert it. The denominator becomes the numerator becomes the denominator, and then we're back to where we were in the last example, multiplying straight across. If we have like terms, well chosen 1 has a value of 1, and then we just simplify the expression. Adding and subtracting rational expressions seems to confuse a lot of students. Now, if we have the same denominator, they're cool with it, but heaven forbid we should be given a fraction where we have different denominators and where the denominator is not a real number, where the denominator is some polynomial and you're asked to add them or subtract them. I find that students need practice on this, so we will definitely be practicing this. Remember, this whole idea is find a common denominator. Here they say least common denominator. You could use any common denominator, but we usually use the least one. And generally, it's just a product of the two denominators. And we're going to multiply by well-chosen 1. See what we've done here? We look in this denominator and say what factor is missing for this denominator to look like this. And what's missing is this factor of x plus 2. So I can't change the value of this fraction. This is important. I don't want to change the value of it. I just need to change the way it looks. Well, how can I change the value of something, or sorry, not change the value of something and change the way it looks? Multiply it by 1. And that's what we're doing here, this whole well-chosen 1 idea. And I'm doing the same thing here. What do I need to multiply this denominator by to make it look like this? So I have a common denominator. And I need to multiply it by the same thing in the numerator so that I'm just changing the way it looks and not changing its value. So you've done this before. I know this is not new information, but I just want to point some things out to you. So again, we multiply and distribute here in the numerator, and here in the numerator we have our common denominator, and we clean things up in the numerator, and that's how you add and subtract rational expressions. So here's another one. So we had these two. It turns out that the least common denominator here, this factors to x plus 1 times x minus 1. So these two denominators have a common factor of x plus 1. So we could say the least common denominator is x minus 1 times the quantity x plus 1 squared. Do you see what they did there? Since this factors and x plus 1 is in that factor, then we don't have to write x plus 1 times x minus 1 times x plus 1 times x plus 1 squared, right? That's going to be too many in the denominator. So what we need is we need a common denominator that looks like this. So what can we multiply here to make it look like that? Well, the only thing that's missing here is an additional x plus 1, right? So that's all we've done, x plus 1, x plus 1. And the same thing here. Sorry, there it is, x plus 1, and then here x minus 1, because it has the x plus 1 quantity squared. So, yeah, and then we just do the math that we already know how to do and simplify. Compound fractions are another thing that seem to freak students out, and I'm not sure why. I think they're kind of fun, but I'm a math nerd, so, you know. When we simplify a compound fraction, what we want to do, here's the process. Whatever the steps look like, this is what we're after. We want to have one fraction in the numerator and one fraction in the denominator. Well, here we have a fraction and a constant, and here we have a constant minus a fraction. I want to find a common denominator up here and make this one fraction, and another common denominator down here and make it one fraction. So what I would do is I would say this was x over y plus y over y. And then I would say this was, let's see, common denominator, x over x minus y over x. And then I would put those together, which is what's been done here, x plus y over y, x minus y over x. Now I have a fraction over a fraction, and I know what to do with that. I just flip the bottom one and multiply straight across, right? It's what I've always been told to do. So I have x times x plus y, I have y times the quantity x minus y, boom. I have a simplified expression. So, I think for some reason, we're done. That shouldn't be in there. Sorry about that. Let's move on. We talked about rationalizing the denominator, but we didn't really talk about rationalizing the numerator that much. Sometimes you need to simplify things, be it the numerator or the denominator, and there's a root in there. And if there is a root in there, you got to think about this whole conjugate radical kind of thing. So let's say we want to rationalize this denominator. For whatever reason, somebody's not happy with it. They don't like that root in the denominator. So what we're going to do, again, multiply by a well-chosen 1. But what we want to do is we want to take care of that root. And the way to take care of that root is to multiply this not by a quantity 1 plus root 2 over 1 plus root 2, because that's still going to keep a radical in the denominator. The whole point of this is, you know, some math police don't like radicals in the denominator, so we got to take care of that. Well, the way I'm going to get rid of that is this whole difference of two squares kind of thing, right? I remember if I multiply the difference of two squares, then I'm going to wind up with something squared minus something squared. And that's going to help me because my inside-outside is going to cancel, right? So we want to remember to multiply by the conjugate, which is the opposite operation, mathematical operation that's going on in that denominator. We could do the same thing if they wanted us to rationalize the numerator. But anyway, you can see this is the difference of two squares. I've just taken the numerator and multiplied it by the same thing as the denominator, multiplied by something that has a value of 1. And then we just clean it up and voila, no radicals in the denominator. So there we go. We're done with that one. So get ready for homework.